Krishna Mission Residential College, Narendrapur, Kolkata, in the year of 2012. PG Physics in Ramakrishna Mission, Vivekananda University, Howrah, Kolkata, and got second rank in the year of 2014. He has done his PhD Professor Rajaraman Ganesh, sir, in Research, Gujarat, comes under Homi Baba National Institute in the year of 2019. His research area is plasma and hydrodynamics. Excellent computational potential, single-handedly developed programming codes from scratch. For example, MPI parallel pseudospectral three-dimensional magnetohydrodynamics 3D, three-dimensional Monte Carlo code for complex plasma systems. Currently, three-dimensional OpenMP parallel electromagnetic molecular dynamics code. More significantly, he delivered a talk on his discovery that recurrence in three-dimensional magnetohydrodynamic plasma in Third Asia Pacific Conference on Plasma Physics, Haifa, China, in November 2019. For this talk, he got under 30 doctoral scientist award by Association of Asia Pacific Physical Societies, Division of Plasma Physics. Currently, Rupak Mukherjee sir is a associate research physicist, Princeton Plasma Physics Laboratory, Princeton University, New Jersey, USA, and he is collaboratively working with Max Planck Institute for Plasma Physics, Germany. With this, I welcome you all for this webinar, and I heartfully welcome our chief guest to deliver the lecture. Thank you.
So, okay. So I got some crude idea about what is about fusion. It's good, and I thought one small thing. Third is that whatever information in this slide is available on Google. Also, I'll be very happy to share the slides. So there are some highlights, and you can simply instead of going through this slide, you can simply go to Google and search it and learn. I want to stress on, you can simply search yourself and get more information, much more information that I have covered in these slides. So yeah, so there is, and also there is nothing to complete, as I mentioned earlier. So feel free to stop me, feel free to interrupt me anytime during the talk. I'll be very happy to take it as a discussion instead of talk. Okay, so first, okay, so I thought I would talk about fusion energy, current challenge, and opportunity. First, maybe directly going to fusion, I'll start with need. Why? Talk will proceed this way, and you can see that I have only 15. Free to interrupt me. Good. So why do we at all need fusion energy, right? Let's look at this. Right. So why fusion? I have just copied this information from somewhere in the internet. So I asked, do you remember this statement from your school text that so this is a, I mean, I'm sure all of you have read this thing of energy, the law of conservation of energy. It states energy can neither be created, only converted from one form of energy to another, right? So when we learned it in our college, probably people, our teachers used to ask this question, then what for friction? How is friction? where does the energy go, and all these kinds of questions. You had some answer, etc., etc. But I hope you all are aware of this. At least from here we'll start, and we'll come back to this statement in the next slide again. But anyway, so right, so this is now we know that energy cannot be created, cannot be destroyed, but only option we have that we can convert it from one form to another. So how much did you means suppose the state Tamil Nadu, how much radiation energy, I should say, how much radiation energy did Tamil Nadu get today from our sun? And so when I keep this dotted things, it means there's a nothing but a Wikipedia link that says link just to find out what is the area of Tamil Nadu. So this is some number, and if I click here, it will open another link. For example, I'm just showing you. So if you just do this, it will open somewhere a link from University of Tennessee, and it says that how much energy did Texas received in one day, and this is the area of Texas. So I just replaced the area of Tamil Nadu that I got from Wikipedia, and that's it. Simple. You get some number, and these are some old numbers. This is in 2008, so I changed these numbers. I got it from some recent sources. So those links are also here. So this is the amount of energy that the whole received today throughout the day. Maybe till now it's 4 for you, 410 or 450. Okay, and how much total power, including nuclear, hydro, thermal, all the power plants of the world, or did all the world use today? So you can clearly, these are the same units for comparison. So you can see these numbers are hugely different, and it's like 30 times almost. So 30 to 40 times. So right. So again, here it will open another link, and mostly these are Wikipedia links. It will open another link, and it will say that how much power. I mean, this is just in support, and you can learn more. Good. So in one day, much of amount of radiation energy within only Tamil Nadu from total power that all the power plants produced. So basically, we can feed the whole world for around 30 days if we could 100% of this energy. But why is this problem? Because the energy is an issue, is a huge issue, and that's this is a personal text, but I think that's the most important for which the countries fight. So if we can solve this problem, maybe we can talk about peace. So, okay. Let's see how much did we spend. So this is one part of this kind of statement, and in the next slide I'm going to just tie up these three threads. Let's now forget about what is the GDP of India. So it's just a Wikipedia link which says what is GDP. So you can just click it and it will open. Right. So you can just learn about GDP when I was in college. But yeah, now you have smartphones, etc. So you can simply go and read up growth, development, and personality, or is it whatever? So crudely, you can think it as the total amount of money of a country. Complicated things, a lot of economics and a lot of things I don't really understand. So what I understand about this is very, very crude, and it should not be taken very seriously. But let's take it in a very rough way. By GDP, we mean that the total amount of resource of a country. Again, I in some units is US dollar. So if you want to transform it to money, Indian rupees, you have to multiply it with by some number like 70 or 75 or whatever. But all of them are in the same unit. So total amount of resource of our country is 2,700 billion. Billion means like 1 million is 10 lakh, and billion is 1,000 times 10 lakh. Right? So 1 billion is something like 1 crore in our system. So it's 2,700 billion US dollar. For example, the total population of India, we call it 1.3 or 1.4 billion. Like 130 crore or 140. Oh, sorry. So this is 100 crore. Sorry, not 1 crore, 100 crore. So 2,700 into 100 crore USD. And how much money in US dollar, how much money did we to buy oil? These numbers are from 2018, I guess. Yes, maybe. I'm not sure, but it's fine. They fluctuate by a very small amount. So how much money did we spend buying oil from all other countries? And that's 120 billion US dollar. This is in 1 year, 2018 probably. And how much money did we actually spend to all the imports? And that is 480 billion. So and all imports means a lot, right? But you can see that the 30% of Indian import came from oil. So when I say 120 billion, it does not really make sense to me because it's a huge number. I have never seen that amount of money. So let's try to understand how much is this 120 billion, that is 120 into 100 crore US dollar, that means into 70. So, right, this is how I can at least get a hold of it. What do we mean by 120 billion? You can buy a gold cube 3 axis, yeah. Gold cube of size 150 cubic meter. This means 150 meter in length, 150 meter in width. And 150 meter is something like, just give a number. Remember your first 100-meter race. So, and this is something like, it's very easy to calculate because you know Archimedes principle and you know the price of gold now, and you number, and then take a cube root 150, right? All right. So it's a huge number, 120 billion. Right, and this is also a very big, handsome fraction of this total resource. So how about if we are energy independent, that is, if, forget about the whole fraction, if we could produce some small fraction of this energy into, we could save this amount of money for all countries. So that's why I'm saying this leads to global peace. So, right. And challenging, why it is even more eyebrow rising, because how much fossil fuel is left on our Earth for around 50 years. So probably you have this information. Somebody says 40 years. I just took a rough number. You can simply click on it like this, and it will open another link. Change live, so you can just, I'm just zooming it up. So if you just go down somewhere, oh, where it is, energy, yes. Is to the end of oil, it's like 43 years, and these are like, they claim that this is something like a live number. This is how the numbers are getting reduced. I thought it might be interesting for you, so I just added this link. So these are for everything, everywhere you can see, and it's so interactive. Okay, so this much is that you can just add these numbers as well. This much is this much days and this other things, and finally you will see of the order of 50 years or so. So 50 years is something in the horizon. It's in your lifetime. It's not that earlier people used to say for the generation. So, right, then why? I've already answered this. Had we been able to convert this energy, whatever radiation energy we are receiving from sun, into electricity, but no, we have not been able to truth, and that is why we are importing, we are buying this much of oil and all other things from different countries. We are spending this much of money, and the world is also running out of fuel. So as the amount of fuel will go down, this price will also go high, right? Because the price depends on how much is available. That's at least one factor. There can be many other factors. And every day our requirement for energy is also increasing. So then why? Because we enjoy or consume more than we can produce or convert. So when I produce, I have to be careful, because in the first slide I mentioned it cannot be produced. It cannot be created nor be destroyed. It can only be converted. So we have the option of this converting this energy. This is one option, which is the solar energy. There are a few other options. But anyway. So that's why I kept the word convert. Or convert, produce means some non-usable form to some usable form. Right. So that's why I mentioned we enjoy or consume. How do we enjoy? How did you consume today? You woke up, toothpaste, and you didn't make it. Earlier, people used to use some. Mostly, people use toothpaste, and to make the toothpaste, right, and you got it from some factory or something. They used electricity to that toothpaste. It has been transported, etc., etc., etc. Well, because of industrialization, things have got cheaper, and you bought means you consumed means you also gave money in the form of something. I mean, right. But in general, in totality, you consumed energy, right? You read the newspaper, so there was some industry, and none of these industries run without electricity. Some industry which took some trees, converted into papers, printing presses, all these things, ink generation, everything. Your morning tea, you had to heat it up. You didn't burn or anything. The gas also. You had to charge your mobile and this talk. So I'm up the electricity because you are viewing it on your mobile or laptop or something, and we need to run this talk smoothly via some internet connection, and there are some internet providers. I lot of cables underwater, and through this or this anyway. So a lot of conversion of energy, loss of energy, and all these things. So we are consuming. So all these are the forms of consumption of energy in this way or that, and we did not produce this energy. Right? We just burnt something. Right? We bought it using our money because of industrialization. So how did we convert this? So we converted, right? We consume this energy. We consume more than we can convert, and how we're running out of fuel. Right? So we got in India. This is the data for India. It's 74.5% from coal and 10% from hydro. You know, the turbines, etc. Well, other things, but hydro means that's the potential energy difference of water. We used winds, 2.9% only from solar. That's really unfortunate. Nuclear fission, not the fusion. Fission is oil and gas, 3.6%. But what will happen? Because I mentioned here that we have only 50 years. So sustainable resources after 2020 plus 50, that is 2070. What are the sustainable resources after 2070? It's hydro, right? The flow of air. Wind is the flow of air. Three. I'm not counting the uraniums because that's also in art, right? So and we are using this, so sometime it will also go out. We'll run out of this. So current challenges: conversion efficiency is poor for solar. This is very true, right? Because otherwise we would have converted this much of energy. This is this much of energy only in Tamil Nadu, and this is world power plant output, 2.86. So conversion efficiency is really, really poor. So I wrote Kovilpatti, but link because I did this calculation for some other cities in India. It's somewhere in MP. So I did not know the exact area of the link. But yeah, I mean, you may have to go for the problem with solar is the conversion efficiency is bad, and that's why you need to put a lot of solar panels amount of charge. Right. So, but purpose, and that's really that all the houses from there about the energy. Problem is the reliability. There's some sunny day and there can be another day which is not sunny. So this is a problem. Then you will not get that much of energy. But you can ask this question. It's fine. We'll convert a lot of energy and we'll store it and we'll use it in the next day. What if I every day I suppose produce twice the amount of my need in my house, and I will store it in a battery. And if tomorrow is not a sunny day, I can use the thing from the battery. But the problem is power storage. We do not really have very good engineering techniques for power storage, which is like cheap enough, I should say. We have a lot of people working in this, and there are very good progress happening. But power storage is not a good solution. So to give you just a bit about just some idea. These are stored in any battery. We produced it and immediately we consumed it. So power storage is costly. That's why we generate and we use, and we do not reliable source of power. Right, and that's why we need you. You mean your expertise. The question is your expertise, but how you can contribute. One way is nuclear fusion. Right, before that, I should say one way is make it much more conversion efficient, and you can understand if you can improve it by a very, very small, it will change a lot of things, right? And there are a lot of people working in it. It's a very, very exciting field. So you guys should definitely consider as a serious problem, and you most physicists maybe also. So you should actually seriously think about solar and power storage. If we can make some cheap power storage devices, that would be really, really, really helpful. Right? Okay. Any long-term, say long-term, that means it'll last for a long period. Safe. Okay, I asked this thing before the start of this talk, and some of you had some idea, I found, but take it granted, fusion, because in case of a fusion, if there is any problem, if there is any disbalance or anything in the where fusion process will stop immediately, and so that's the plasma will not sustain, and that's very, very safe. The process will, it will not cause any burst or anything. It's so simple. Yeah. And green, I have put a link of this carbon footprint here, and I strongly suggest that you go and read about this carbon footprint. These are very, very important, because you can get some idea about how we are actually polluting our nature. Yeah. You guys should actually, so there are now concepts like zero emission houses, so that every house try to make their house in such a way that they do not produce any carbon, at least like they produce equal amount of oxygen also. So they keep plant, etc. And we are burning these fuels and etc. So these create a lot of coal. In India, last year, energy 5% of electricity from coal, and we are adding this carbon nature. And the problem with it is it does not run out immediately. Switch off the source. It's years, 10, 15 years, and more than, then slowly decays. So it's a huge problem. Right. So any long-term safe and green solution for your old age? Yeah, there is one solution, and the solution is basically this equation, E equal to mc squared. Don't worry, I'm in any of my slides, there will not be, there may be one more expression, but that's Ampere's law, you all know that. So, right, so there will be no more equations, etc. So I hope all of you know this, E equal to mc squared, and the binding energy, I don't know if you still remember. Let's look at that. Okay, let me blow it up. Right, binding energy curve was this curve, and you can see that so this is with mass number, binding energy per nucleon. So this is yield from nuclear fission. This is this amount of nuclear fission, and yield from nuclear fusion is right, is larger than earned from nuclear fusion. Okay, and I hope you know about isotopes. That's fine. So what is the plan? The plan is you fuse two hydrogens, some isotopes of hydrogen. One will have one proton and two neutrons. Sorry, one proton and one neutron, and another will have one proton and two neutrons. You fuse them. One is called deuterium, another is called tritium, and you just fuse them, get a helium and a high energy neutron. The idea is, so where you are in this binding energy curve, if you're here, you are somewhere here, you fuse of the order of here, and here energy will release. And this number is talk about this number anyway. Where will you get deuterium? In seawater. Where you'll get well, tritium. Tritium is difficult, but and we are in seawater, I mean, like the etc. And also in our lithium is not a big problem obtaining, and we have in art we have a lot of seawaters, and we can get deuterium, tritium from there, and it will produce helium, which is safe. It does not emit any carbon, and we get a neutron. And what do we do with the neutron? The neutron just comes out and then hits somewhere. And hit means it's just like a collision, scattering Coulomb. Sorry, it's just a like hard sphere collision. And its kinetic energy, which is this amount of energy, 14 mega electron volt. And this kinetic energy is converted into some form of heat energy. And the rest of the things are the same as the nuclear fission reactor. In the nuclear fission reactor also there's some neutron, which much less energy, that will come out, heat some wall, the wall pass water will be vaporized, water vapor through some turbines, and you just keep the, so the technology is developed. Something similar as like the wind. Right, and how does it solve the energy problem? So this is an exercise for you. Try to convince yourself from this number. Well, there's a hint that 1 mega electron volt is just this small amount of number, just kilowatt hour. This is 30 times the remaining lifespan of our sun. And I didn't calculate it. I just got it from some link from somewhere in Wikipedia. And if you go below, right, let's go a bit down. Oops. Right. So in energy sources, you can see that there are some talk about this, that with 150 years, 1 billion is, I mentioned 100 crore. 50 billion years is close to 30 times the remaining lifespan of the sun. From somewhere in Eric Christian here, NASA, there are some references and all the calculations are hopefully right. So this number is not from me, and the best exercise is probably the best thing is to tell you that get this number, get how much uh, tritium can we get from seawater. You can just get it from Wikipedia or somewhere. Again, how much deuterium can we get from seawater? Convert that and divide it by the present need of our world, energy need of our world, and then you will be able to get it. And this is huge. And yeah, why it is huge? Because see, the sun is every day doing this nuclear fusion, right? And the sun amount of everywhere through the space, and this amount of energy is 130 terawatt. The energy that this is also the fusion energy that so the everywhere only a small solid angle subtended at fallen there. Nuclear fusion of that. Right? Then why not? Because challenges. So yeah, we need your expertise. Let's delve into the technical questions. Yes, I asked, have been achieved? Mentioned earlier that yeah, it's in the core of this Earth, but well, no, on the Earth crust also. We do it almost every day in labs, in all the lab, including like not in the same lab, but if you count all the laboratories around the world, yes, we do fusion every day. So why? That's why I said, then why? Why not? Because again, the problem is the same. The conversion efficiency is not good. So the sun earlier that yeah, it's through fusion. It's the same process as I mentioned in the last slide. Then why do not we learn or copy paste? Is producing the fusion. Why don't we copy paste the idea from our sun? The fusion is through hydrogen, and we are using, instead of hydrogen, we are using deuterium tritium because this amount is more for deuterium and tritium. We could have used hydrogen, but then this instead of 14, it will go down. It will be some number. So we can actually produce a lot of energy, right? To get some idea about how much is this, imagine this like a canvas, like the cricket ball, and you go 10 meters away from it, and you put mustard bead. That's Earth. So now imagine the sun is like a canvas ball or like a cricket ball, and it's radiating energy everywhere around it. And imagine the small bead in the 10 meters away from this ball. And now the Tamil Nadu is a very small portion. And right, so the solid angle subtended towards the sun, that much energy is falling there, and that's this 130 terawatt per day. Right, and if we could achieve it here in Earth, it will be, that's why it is huge, right? And we are actually doing some other equations for which this yield is even higher. So it's hot. What we mean by hot? It's 50 lakh degrees centigrade at the core. So to get some idea about what is this number, 1 crore 50 lakh, it's very big. So I just compared it the temperature of a flame. A flame, typically, you guys will know better than me. There are different kinds of flame, but this is probably for white flames. This is 1,500 degrees centigrade. And this is 1 crore 50 lakh. And how about our laboratory devices? They're hotter. They're like 10 crores. So clearly, this is probably now you guys very clearly understand that you cannot simply burn a fire because the fire will be of the order of this. You cannot simply burn, like initiate a fire. So that's why I told that fire is a very cold plasma. And hit something into 10 crore degrees centigrade. It's difficult. So how do we do that? Thanks to our engineers. So there are some links. One, ohmic heating, Ohm's law, right? There are several other techniques. This is called electron cyclotron resonance heating, ion cyclotron resonance heating, neutral beam injection, and a lot of other techniques, modern techniques. So how does sun fuse? At 1 crore 50 lakh degrees centigrade, everything is in plasma state. I remember something I will tell you when I will talk about plasmas, but I don't remember now. But anyway, you can what did I say? So it fuses 50 ton of hydrogen plasma each second to produce helium and energy. The same formula, E equal to mc squared. So coming back to this question, we can simply learn, or we can simply copy paste the idea from our sons. What is the problem? Why we are still having so much fight about different nations? The question is, you can ask question is the answer. Why is the hydrogen in the sun basically confined? Right? This if you will be able to answer this. Why have a radius? You know that the sun has some radius, right? So imagine you take a jar of air, you go into the space, you open the bottle. Do you think that the jar of air will become something like a sphere, which will have some radius, and outside that radius, the density of the air will go to 0? No, it'll expand and it will pervade into the space. So why it is not happening for our sun also? Why does sun have a radius? Why is this is basically the same question physics wise. Why is the plasma confined in sun? So if we can confine the plasma in our art the same way, the problem is actually solved, but we could not. That's why we are talking about different technologies of this plasma confinement. The question is, why do we need to get those technology? Why can't we copy the same technology that the sun is using? Using something very subtle, which is very natural for sun. For us, it has a huge gravity. It has a lot of mass. So the amount of air in a small bottle, if you're taking from here to the space, you'll not have enough. Why the mass is so great? Well, I just reiterated the same thing, because it is massive. So to get an answer, you have to remember Gauss's law. You remember something like, let's do it in a simpler way. Definitely in your school you did a calculation like, if you go down into a mine, the value of G goes down, something like that, probably. I'm sure at least physics students have done that, because I also did. I'm from physics background. But definitely in schools, where did I study that? In schools or in college? I don't remember. But anyway. Or if you go out of our Earth, why does the value of G, the acceleration due to gravity, fall down? Why it is highest on the surface of the Earth? It's the same solution, same thing, that the total mass contained within the. Right, so because of this mass, because of this huge mass, and that's just, you can get the idea from the same Gauss law. Because of this huge mass, the plasma is confined. Exercise, you can work out the critical radius of any star. What will be the radius of a star? I mean, radius means the total amount of mass from it, what amount of mass is needed for a gas to be a star. Star means I just mean that it will have a radius. Have you heard of Chandrasekhar limit? Well, it's not directly connected, but yeah, radius for neutron stars. And instead of radiation pressure, there was electromagnetic pressure, but a few other things. But it's essentially the idea behind this thing is probably the same. So if you can answer this question, you'll be this also. It's just a Google of right. But we do not have that much of mass. Sun is massive. We do not have that much mass to confine the plasma. So how will we confine it? Back to your first year. Do you remember electrodynamics? Motion of a charged particle in a magnetic field. How did one particle of a charged particle, suppose an electron used to move in a magnetic field? It used to gyrate, right? So if you have a magnetic field, the charged particle cannot leave the magnetic field. It will have to go wherever the magnetic field is going. So we also do the same thing. So clearly we cannot confine the plasma using gravity because we do not have that much of mass, but we can confine the plasma using magnetic fields, right? And that's what we actually do in our labs. We try to confine and heat it up to 10 crore degrees centigrade, which is like 10 times or whatever, several times the core of the sun. And we try to make the fusion, and every day people try to make the fusion. And there are different twisted toroidal magnet. So how do we confine? We create some twisted toroidal. When I say bottle, what do I mean by bottle? It says just that the simple, divergence of B is 0, right? So if you have a set of magnetic field lines, you will have to close to it. And instead of closing to its, when it is closing, add a twist in it. The twist is very important. We add a twist and we make it a toroidal. So we make a torus, twisted torus of twisted toroidal magnetic fields or magnetic bottle I mentioned to confine the plasma. And there are different toroidal twists. One is called tokamak, one is called stellated. There are a few. So the problem should be solved. This kind of a toroidal magnetic bottle, we can confine the charged particles. That means we can. All right, now I remember. So by plasma, I mean very simply, I mean that something like a charged gas, like something like a charged particles, a collection of charged particles, which can show some collective effect, etc. Let's not get into that. So problem was almost solved, but the problem is, till now, we are unable to make a foolproof magnetic bottle. The errors in the magnetic field lines generated via the current carrying coils, you have to create several current carrying coils to generate this magnetic field, right? Otherwise, how will you generate strong magnetic fields? You just simple, the ampere, it will generate a magnetic field. So, but there will be errors, right? Of course, you have to measure the error and you'll have some tolerances. So the errors in the magnetic field lines generated by the current carrying coil should be within the tolerances. And we need you, that's fine. What will happen otherwise? It's not good because it's 10 crore degrees centigrade plasma, it will spill out. Okay. So left, and don't worry, the slides, so this slide and the next slide is the important. Rest of the slides are very simple. You can simply, the rest of the slides are nothing but some hyperlinks. So you can simply click on the hyperlinks. These are some names of industries and things like that. So all the slides and the opportunities are just some names of the industries. I can share the slides. You can just have it, and So that's not important. So we don't really need to cover any of these things. Neither. Most important part is probably this slide and the next one, this one. If we can cover this within our 1 hour schedule, that's good enough. Good. So let's, how did we draw this magnetic bottle? So we can skip the rest of the slides, that's fine. Let's try to concentrate on a magnetic bottle. So let me keep this picture open in one of these. Yeah. Now let's see. Stainless steel torus. So, right. Shown here. So these are the picture of the plasma. So the torus is somewhere. So you can think this as the torus. I hope you can see my cursor. So you can think this as the torus. This is basically the plasma. So imagine a stainless steel torus, like a bicycle tire, lying horizontally, right? Lying horizontally. And current carrying poloidal rings. What do I mean by poloidal rings? These are the poloidal rings, right? You can think it as simple rings of circular shape. As of now, it's D-shaped because of some other optimization. So there is a torus of like this, and there are some poloidal rings like these colors around the torus, and a vertical solenoid through its central axis. Right. So this is the vertical solenoid through its central axis. Okay. To make a fusion, to confine the plasma in the last slide, and to make fusion to get that amount of energy, what do you have to do? These 3 steps, all that you have to do. You feed hydrogen gas, no plasma, don't worry, you don't have to create plasma now. Hydrogen, and for deuterium tritium, yeah, you can feed deuterium gas, and you can like put some lithium at the inner surface of this stainless steel torus. It will it will generate the tritium. So as of now, let's hydrogen gas, because you can also achieve fusion through hydrogen gas as the sun. Feed hydrogen gas at low pressure in the torus. So first is you have to create a high quality vacuum within this torus, and feed some hydrogen gas, run some current through the poloidal rings, right? So these rings, these are the poloidal rings. So you have to run some current through this poloidal ring. What it will do, if you run some current in this through this poloidal ring, it will generate a toroidal. So this is the poloidal direction. Just a quick query. Can you cursor, the one that I'm moving? Otherwise, there's no meaning of this, that, etc. Can you guys see my cursor? Please?
Yes, sir, we are able to see your cursor.
Perfect. Okay, great. So these are the poloidal rings, and this is the toroidal direction. So if you run current poloidally, right, it's from Ampere's law. If you run current poloidally, it will generate a current this way, right? At least for this, it will generate a sorry, not current, magnetic field. If you run current poloidally, it will generate a magnetic field this way, and then again in this poloid, poloidal direction, if you do it, it will create a magnetic field this way, and this is how you just cover. So this is how you generate a toroidal magnetic field. So we get toroidal magnetic field from poloidal rings, and you have to ramp up high current through the central solenoid. So through this solenoid. Okay. So basically, this is something like a transformer action. Well, I don't transformer core. So what it will do? Okay. So all set. I mean, this is all the things that you'll have to do to get a fusion, and that's what is generally done in all the tokamaks all over the world. Change of flux through the torus will induce toroidal through change of flux through the torus. If you ramp a high current through here, it will cause it's something like an induction. So it will induce a toroidal current through this torus. It will induce a toroidal electric field, I should say, instead of current. And here I am saying that it will generate, but we mentioned that we have hydrogen gas, we have neutral hydrogen gas. So if you have neutral hydrogen gas, there can be electric field, but why there will be a current? Because the current needs a free ions or electrons to move, right? I should get rid of this. This toroidal current appear. And then this toroidal current will give rise to a plasma. How? Well, we are just going to talk about these questions in the next slide, and that's all. That's all you need to know. Well, and one more thing. If you have a toroidal current, which I mentioned here, this is this toroidal current, it will also generate a polar rings. These were poloidal rings, and here I am talking, and these poloidal rings gave the toroidal magnetic field. And here I am talking a different thing. I am talking about poloidal magnetic field. From poloidal rings, we generated toroidal field, and here it is poloidal field from this toroidal current. It's just the opposite. It's just different. And how is the simple Maxwell's equation? So, right. So, poloidal magnetic. What do I mean by poloidal magnetic? Poloidal magnetic field from this toroidal, this short way, this way. Fields. And we had this toroidal magnetic field from poloidal rings, the earlier one. So if currently, so what we'll have these poloidal fields and these toroidal fields. If you add these two, it will generate helical magnetic fields, right? So this is the helical magnetic field, whatever they have shown, the resultant helical field. This bit exaggerated first. So what? Why do we at all care about this helical magnetic field? Okay, let's go to the next slide. And that's it. So we learned how does this toroidal electric field was generated. This is from transformer action, this one, right? And we are trying to understand why will there be this toroidal current? Toroidal current, why? Well, we had an electric field in a neutral, trying to understand why that will induce the current. Idea about how much ions or electrons are there in room temperature. Well, if you do not have, you can simply go to this link. There's one person in 1920 named Meg, and he gave an equation called Saha ionization equation. And the equation actually charged particles are there. You can. That's a very, very small number. Very, 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 very small number. So, well, but still there are right. They're very, even though they're very, very small in number, there are some free charges, and you have a toroidal electric field already generated from the transformer action. So you have a free charge in an electric field that will give you the current, right? So this will give you the toroidal current, but it's a very, very feeble current, very, very small amount of current. And I mentioned that from this toroidal current we will generate plasma. For plasma, you'll have to generate a lot of this. And how? So this one, now we understand how will we get this toroidal current. From this toroidal current, we'll generate plasma. How now? The free ions in the electric field, these ions are charges. These charges will accelerate in the electric field, because if you have an electric charge, free charge in an electric field, it will accelerate. It will gain more velocity. It will collide with the neutrons. neutrals. So further, and then if this electric ion will also accelerate, and this is how this will generate an avalanche. Lot of something like a chain, and that create the plasma. Okay, so we have plasma, and then why is this helicity is so important? Well, it's very important. The toroidal electric field, sorry, the toroidal magnetic field from colloidal rings were not uniform, right? Yeah, recall Ampere's law. So I'll just borrow a slide from one of our teachers, Matt Linderman. And now you can see this picture here. So these were the colloidal rings. And if you zoom out this part, it has this kind of a, well, I'm over by 5 minutes, I guess. So the strength of magnetic field is more here, and the strength of magnetic field is much less here. Such a gradient in this magnetic field, you're generating this field from some current, right? So what happens is in such a gradient, in such a magnetic field gradient, the particles drift. This is how the particles drift, and this drift is dependent on the charge. The Q factor is sitting here. I hope if I'm blowing it up, yeah, this factor is here. So this means that the direction is different for because electrons and ions will have different charges. So what will happen? Electrons drift downwards and ions drift. Beautiful link from Wikipedia. For positive charge and negative charge, if you have a gradient in the magnetic field, how will the drift happen is written here. You can because if there is a drift, there will be local electric field and a lot of issues will happen. Yeah, you rotate it. And how do you rotate it? You generate a helical that will generate. So what will happen is like magnetic field. If the ions are going upwards in the next turn, like here, if the ions in the next turn they will come downwards, and then again they will try to go upwards, and this is how it will cancel. Okay, so this helicity or twist got right. This and note that this helicity or twist has got naturally generated. You may have to think from what, how did I make this comment that it has got naturally generated? Because we did not add an extra coil or anything to generate this helix. This helix got generated from this toroidal current itself. We needed the current to generate the plasma, and the plasma automatically confined itself by generating this helical magnetic field. So now you have all basic theory of plasma confinement ready for at least for one model, which is the most used model. Yeah, the fusion energy is on the horizon. Is it okay to go over for like 2 to 3 minutes? Hearing me? Hello? Okay. So, but after all this, the harsh reality is this plasma, this 10 crore degrees centigrade plasma, does spill out and touch the metal vessel. With this, I mentioned about this stainless steel vessel, right? So we need cryo. India is responsible for and neutron, maybe neutrons. So I will talk about what is ITER in short, and I have some links where you can actually find it out. So we need experts in superconductor technology, because we need to cool down the outer vessel, right? To cool down the coils and mechanical engineers, yes, of course. We need to handle such thermal stress, because if the plasma falls, it will generate a lot of thermal stress. So we need. You can skip this. This is what I do. A brilliant idea is you create a local turbulence and spread the heat load in this metal vessel where it is falling. So, but then we need experts in turbulence, experts in fluid dynamics, aerodynamics, but it's a magnetized plasma. Yeah. So the basic properties are a bit different. So we need physicists as well. Another problem is the helium. You will generate helium. So, and this is a plasma. So this is a mixture of helium and deuterium and tritium, right, in the core. And the helium needs to be extracted. So how can we keep deuterium and tritium confined in this geometry and get helium extracted in real time, 10 crore degree centigrade plasma mixture? Well, so we need to draw better magnetic geometry to confine this plasma. So we need computer engineers, better softwares. There are already a lot of beautiful magnetic geometry, but yeah, sorry. These computations, the course and it takes money. We need high performance computing experts, we need better algorithms, we need people who are computer experts in testing algorithms, its scalability. It will generate neutrons. So we need robotics, experts in robotics, remote material handling. Every time a person cannot enter into it. And another about ITER, I will talk. ITER is just one more tokamak, and it does the same way that I mentioned earlier in the fusion technology slide section. It needs to generate 46 kiloampere current in a huge solenoid. You can get the from this link. This is the current which will. What this current will generate, it will just generate the twists in our magnetic bottle. So we need electrical engineers. Right. We need to, the vessel that needs to be in some sort of a low pressure, which is like 10 minus 4 Pascal. So we need to keep this vacuum keep this amount of vacuum for 8,500 cubic meter of volume for several hours. Right. So we need private company involvement, feedback control of plasma and all this stuff. We need a lot of engineers. Just if I'm allowed to go into more overtime, these are just for few links. So what is ITER? ITER is a tokamak. ITER, how does ITER fuse? ITER fuses the same way that I mentioned in this section. The same physics, same, and sorry. Oh, yeah. Everything is same. What are the countries involved? There are 35 countries. China, European Union, India, Japan, South Korea, Russia, United States, and others. How much is the cost of this ITER? Where it is done, the experiment is being done at somewhere in France, Cathédrage. The full name of ITER is International Thermonuclear Experimental Reactor. How much is the cost? So it will start generating the plasma in 2025. This is 2020, 5 years after this. And US estimated the construction cost is $65 billion US. Well, how much is this 65 billion US dollar? I gave one example of this US dollar, billion US dollar in the form of the gold cube. Well, let's look at this from physics experiments. The LHC, have you heard of this? At least for physics students, most probably nowadays everybody has heard about Large Hadron Collider. This is just a link of a Large Hadron Collider. And how much money did we spend to build this Large Hadron Collider? It was 4. And how much is the ITER? It's 65 billion, huge. And probably nowadays a lot of you know about LIGO, right? The gravitational wave detector. To build this, we spent 1.1 billion US dollars. And now you can compare the huge, right? There are more tokamaks currently under construction in different countries, and 7 more planned in different countries. And currently operational tokamak, yeah, so we have a lot of tokamaks. These are just some names. I mean, like there are a lot more. And these links are there. So if you just click here, it'll open the link of this tokamak or this project. So we have one here in Princeton, Nationals, anyway. D3D, ASDEX upgrade, JET in UK, ASDEX is in Germany, D3D is San Diego. East in Hefei, K-Star, SST, Aditya, U for upgrade. So we have a lot of this currently operational nuclear fusion reactors. And also in India, and we have really good results from here. Sorry, this is somehow my, yeah. There was in earlier days, there was another PR in Princeton. That time it was the highest 10.7 megawatt. And in JET, and in 1997, UK, they produced 16 megawatt, which is the world's highest. The input was 24. So you can clearly see that it's a loss, right? 24 megawatt of power, 16 megawatt. If you divide this 16 by 24, you will get a Q. This is called Q value. It's 0.66. And how much we are planning to get from ITER? It's 10. Instead of the 6, we are planning to get 10. It's a huge. There are a few other fusion concepts. One is national ignition. If some of you are expert in lasers, to see this link, national ignition facility. I covered something called magnetically confined. Another is this inertia. Another magnetically confined is stellarators, I mentioned. So that is also a twisted magnetic field, but the twist is subtle in. And the Germans actually spend around $1 billion US. National NIF has US funding. So there are a lot of. And private industries. Google, yeah, they also spend money. They have a company called TAE Technology, Tri-Alpha Energy. Tri-Alpha, now you know, right? Deuterium, tritium. So Tri-Alpha Energy, California. Another company, private company, called Tokamak Fusion in UK, Agni Energy in Washington, Commonwealth in Cambridge, General Fusion in Canada, and many other startups. Right? So you guys should actually think about it. A lot of opportunities. If you are still with me, bearing my no picture, no movie slides, this is for you. You can open it and you can watch the small 3-minute video. Oh, sorry, let's mute it. Yeah, so this is what the ITER is in France. And the picture is shooted from a drone, and so this is what is actually happening. And this is very latest. This is June 2020. Right. So this is what. So they are giving. This is the live update. Not live. Like this is the last 2-3 months from ITER. This is under construction. So right. So you can see what is happening in ITER, and clearly you can understand that there is a lot of technology needed. So we need. This is not a job of 1 or 2 persons. This is a mega project, and that's what is happening. We need a lot of engineering for this purpose, right? So these toroidal field coils, poloidal field coils, and all this stuff. So these are coming here, right? This is the campus. This is the ITER campus in France, and this is what happens. They were making. Right, so that's the link of the mega project, just in case. Okay, so they are like, so the drone is flying upwards, and right. I'm just kidding. This is from the official. So, right, so you can see a size of human here. here the size of humans, and this is the size of the things. So then this is about of the project. I don't know if you could see this. Could you see the movie? Sorry. Could any of you see the movie? Because I opened it in a different browser. Maybe I should.
No, sir.
Oh, sorry.
Movie is not visible.
Okay. Sorry about that. Let's go this way. Now, do you see the movie?
Yeah.
Okay, you should have yelled up. Anyway. Okay, so let's go once more. So this is the campus. Why did you not yell up? Okay, so this is the campus. This is the size of the technology, as I mentioned. I'm repeating myself. Okay, so this is the live update from the drone. That's what I was talking about. Okay, so yeah, so this is the size of the humans, you can see. And right, so this is the campus from drone. This is the whole experiment, and this is the live updates. This is the campus. You can see that a lot of technology is in. This is the movie I was showing, and I was telling that you just heard my voice. That's bad. Now you are seeing my movie, right? Can any of you just speak up? I can't go to the.
The screen is visible, sir.
You are not seeing the movie?
No, sir. You have to play, sir.
Now?
Only screen is visible. You have to play that video or something like that.
I am playing this. Let's forget about it. So the links are here. Also, this teacher construction link is somewhere here. You can simply. The Google Meet is not allowing me to do the live focus of this video. But okay, so you can simply click this link and go to YouTube. These links are videos. So let's skip that. So, or also, if you just simply search this keyword in YouTube, you will get a lot of videos of construction of features. So you can make yourself convinced. So right, so that's it from me. Okay, if you have any questions about tech still now, because I know I'm seeing over time, but yeah. So that's the end. Thanks.
So thank you, sir. So dear participants, if you have any doubts, speaker. Now the session is open for discussion.
Yeah, good evening.
Yes.
Sir, actually, what is the characteristics of plasma, sir?
Yeah. Yeah, I can hear you. Yeah. Please ask the question. Yeah, I can hear you. Yeah. I heard
What
that
is
you
the
told
characteristics
the
of
characteristic
plasma?
of plasma.
It behaves.
That's what I heard. Sorry, can you just repeat? Looks the voice is getting cut. So maybe you can post the question in the chat window, and I can see the chat window, and I can tell the answers. Let me just simply go through the chat window, the questions. I don't see any question. Okay, so there are lots, etc. But I did not look up the. Okay. Video is still paused. Visible feedback. Okay. What is the characteristics of Plasma. Okay. Right. I did not answer this. I remind me anyway, before the talk started. So on zeroth order, you think it's a collection of charged particles? Neutral gas, you know how it is neutral? Anyway, nothing is neutral because you have some electrons and protons. So you have a nucleus and electrons moving around it, and so overall, if you go beyond the scale of a nucleus, it's neutral because the charge. But if you put some more energy, some part which is electrons, and so this is how the gas can be charged if you put a lot of energy, and this is how they generate a plasma. This is not the everything about plasma. To generate a plasma, there has to be some few other things. For example, at least the collection of charged particles be able to screen themselves and all these things. And the screening will have to have some leaks, etc., which will actually allow you to have some collective effects such that it supports waves or things. Different kinds of plasmas, right? So there are several standard definitions in several different textbooks: quasi-neutrality, collective effect, and all these things. But these are general definitions that is not maintained in non-neutral plasmas, but they do exist. And anyway, okay, right. So right, that's the general characteristics. Yeah. Spills out and we need to handle it. So why can't we make the plasma flow over and over again without? Right, exactly. That's what we do. A good question. Good question. Is you have told that the plasma spills out and we need to handle it. So why can't we make the plasma flow over and over again without spilling? Do this thing. Let's go to the again. Yeah, here. What happens is plasma exactly follow this helical field line, and that's why it is helix. That's why it is a torus. We took a torus so that it can go over and over again. It goes over and over again. The problem is yes, that's true. Some other problems in the next slide. You have to exhaust. You have to keep an exhaust such that the helium, you can extract the helium in real time, right? Instead of you cannot this whole pure torus. If you have a pure torus, then you cannot extract fusion by after fusion, whatever helium will generate. You cannot extract. So you have to actually put some openings into this torus. So typically, there are different types of openings. These are called diverters. A lot of research with these different diverters so that we can actually extract the helium. And whenever you just try to do that, it creates a lot of problem because when the helium is coming out, it does not come out alone. Right. So but this is you. In real time, because You are true that the plasma moves like in this toroid, and that's always, but there are losses from here, and this small amount of loss that makes our life hell. Okay, is that okay with you? Whoever had asked this question, is that okay? But there are a lot of other progresses with this. How do you put these diverters? A lot of different geometries for diverters, and a lot of research. And some of us have worked on those aspects. Good. Any other question? If you have a bad internet, you can simply post the. Sorry, I can't really hear you. Yeah, did you? Your voice is getting cut here.
I think we can conclude the session.
Okay.
Yeah. So I request sir to deliver the vote of thanks.
Thank you, Anurag sir. So myself. So first of all, I would like to thank Dr. Rupak Mukherjee for his wonderful lecture, so which enlightened us in a new dimension, and we had a great interactive session too. Thank you, sir.
You're welcome.
Next, I express my sincere gratitude to our management director and principal for providing an opportunity to conduct this webinar. Then I thank our head of the department, Dr. M.A. Nilagandan, for his support to conduct this kind of webinars. I thank my fellow colleagues for their efforts to organize this webinar. Finally, I thank all the participants from various institutions who have listened to this webinar. Once again, I would like to thank you one and all. Thank you all. Thank you.
Thanks. Yeah, happy Engineers Day. Just Professor Naraj, if you want the slides, I will be happy to share. Yeah.
Sure. Yeah.
You can send me an email or whatever. I'll just send you the PDF.
Yeah.
And the
Sure.
PDF contains links, so hopefully all the students will get everything there.
Yes.
Great. Yeah, sure. I'll share.
Thank you.
Otherwise, I'll anyway put it in somewhere in the open internet so that everybody will have access.
So I will share your.
I'd be happy.
Yeah. I will share my
just
email ID.
Mail in my in any of my emails, and I'll be happy to share. Yeah, you can write to me if you have any questions or comments, and if I know the answer, I will. Okay, so is this I lost the chat. Let's see. Is this your email?
Yes, sir.
annaraj.sh@nec. Let me just copy this and Control C. Yeah, or anyway, we'll fix this later.